Okay, so now we've seen three examples of elimination reactions. We've seen E1, we've seen E2, and we've seen dehydration. Dehydration is kind of a fancy version of the E1 elimination. But either way, we've seen three different examples of it: E1, E2, and dehydration. And so now the only thing we have left to talk about this week is how do we know which hydrogen to remove? Because oftentimes we'll have the choice of multiple neighboring positions where hydrogens exist. How are we going to know which one needs to take the hydrogen from it? There's a rule that will govern this. The rule is followed most of the time. Of course, this is organic chemistry, so there's always going to be an exception. But for the most part, this rule is going to be what guides us. So let's talk about that. Zaitsev's rule. So the Russians love their carbocation chemistry. They love their double bond chemistry. So Zaitsev is the one who came up with this rule. Zaitsev's rule says in an elimination reaction, and this is any type of elimination reaction, E1, E2, or dehydration, the hydrogen will be removed from the most substituted neighboring carbon. And the reasoning behind this is that by removing the hydrogen from the most substituted neighboring carbon, it will create the most stable alkene product. So an example, let's say that we have something like this. This is an elimination reaction. We've got a strong base in here, right? So anytime you see that alkoxide in there, we have a strong base. This implies that we will be making, this will be an E2 elimination, right? And so now we have a choice. We can take the E2 elimination, can remove the hydrogen from this position, or it can remove it from this position, because these are the two carbons that neighbor the leaving group, right? The leaving group is here. We have to take the hydrogen from the neighboring group. And so the choice is between this position, secondary carbon, or this position, which is a tertiary carbon. Zaitsev's rule says that we will take the hydrogen from the tertiary position, make the pi bond, and kick out the leaving group. And so that the product that we'll get will be only this one, right? So we'll only see this product, right? We will not see where the alkene is over here, not observed. And the reason behind that is that this product is actually more stable, right? We have more substituted alkene, it's got more stuff surrounding it, and so it's just going to be more stable. So we get this one. Okay. So this is Zaitsev's rule on E2 elimination. It also follows for E1 eliminations, right? If we were to do an example of an E1 elimination, let's take, and we'll just do this in water and heat, right? As we heat this up, right, so we have a poor base, a weak base, and so this is going to be an E1 elimination. As we heat this up, the bromine will leave, we'll get a secondary carbocation, and now we have a choice. We can take the hydrogen from this primary position or from this secondary position, right? Those are the two positions that neighbor the carbocation. Zaitsev says that we will only take from the more substitute position, so we'll get a final product that looks like this, where the alkene is here. See this one only. We will not see this one, not observed. Right? We won't see that product in there. So Zaitsev's rule is usually pretty straightforward. You find your leaving group, look at where the hydrogens are. The only potential issue is if you have rearrangements occurring, right? So let's look at an example where we have a rearrangement. And just for good measure, I'm going to make this dehydration as well. I have probably used this example somewhere else along the way, but whatever. As soon as we see an alcohol and H+, this is an E1 dehydration reaction. And oops, I need one more group on here. I'll put a methyl group over here. Okay, so this is an E1 dehydration reaction, and so we can follow this through. Our alcohol is the base. It comes and gets the H+. We create our activated alcohol here. That activated alcohol is going to leave. And this is a lot of different things going on in one mechanism because we're going to get a secondary carbocation, but immediately we notice that we have a secondary cation next to a tertiary position. And so this is going to rearrange. That hydrogen will move over. We'll get a tertiary carbocation, and now at long last we can do our E1 elimination, right, where water is going to come to remove a neighboring hydrogen. We have three possible neighboring hydrogens. We can take a hydrogen from there, we can take a hydrogen from there, or we can take a hydrogen from here. Right? Those are the three positions neighboring our carbocation. So we go through and catalog each of these positions. We have a secondary position here, we have a secondary position here, we have a tertiary position here, and so water is going to take the hydrogen from the most substituted position, this one right here, and make the pi bond. This is our E1 elimination, and the only product that we get out of this is this one right here. Zaitsev's rule tells us that this will be our main product, right? And that comes from forming the carbocation, rearranging, and then following Zaitsev's rule to take the hydrogen from the most substituted position. So we don't apply Zaitsev's rule until we're ready to remove the hydrogen. So when we make our carbocation, we have to first look and make sure that we don't do rearrangement. So please don't forget about rearrangement, right? It always jumps up when you least expect it. So anytime you make a carbocation, first thing you look for, does it rearrange? If it does, then do that rearrangement and then worry about the SN1 or E1 reaction that's going to happen. If you're doing E1 elimination, then you have to follow Zaitsev's rule. Okay? There's one last thing to say. It's the exception to Zaitsev's rule, right? The exception to Zaitsev's rule, come on, give me a new slide here. Only occurs in SN or E2 reactions. The exception to Zaitsev's rule. Only in E2 reactions and only using one particular base, and that base is potassium tert butoxide. So if you have a tert butyl group with an oxygen attached to it, so this is potassium and O minus, and then you have this great big group attached to that oxygen there, right? So KOTBU is how it's most commonly written. This is it drawn out. And the reason behind this is such a sterically repelling base that it can't get in and take a hydrogen from the most substituted position. And so potassium tert butoxide always removes the hydrogen from the least substituted position. Oops. So going back to our previous example, if we had this compound here and we took it and used potassium terbutoxide, right? You would immediately recognize potassium terbutoxide as the exception to Zaitsev's rule, and you would take the hydrogen from the less substituted position, the primary position, and we would get the opposite product from before, where we get only the less substituted alkene in there, right? So potassium terbutoxide is just a nice way to kind of get around Zaitsev's rule, because sometimes you want your alkene to be in a different place, right? So that will allow you to avoid Zaitsev's rule. You'll take the hydrogen from the less substituted position, and you'll get a different alkene product than you would if you followed Zaitsev's rule. But the only exception to Zaitsev's rule is potassium terbutoxide, and if you used potassium terbutoxide, it's a strong base, so it has to be an E2 elimination mechanism to do that elimination, right? So if you're doing E1 eliminations, dehydrations, anything like that, it will always follow Zaitsev's rule. There are no exceptions to that, right? If you're doing E2, you can get around Zaitsev's rule if you use the one special base, potassium terbutoxide.